Welcome back to Everyday Nuggets. Dry ice, the fascinating solid form of carbon dioxide that sublimates directly from solid to gas, creating that mesmerizing fog effect we've all seen. It's used in everything from food preservation to special effects. But have you ever wondered exactly how this mysterious substance is produced? Today, we're going to dive into the fascinating process behind dry ice production, exploring the science, manufacturing methods, and unique properties that make it such a valuable material. Dry ice is solid carbon dioxide with the chemical formula CO2. Unlike regular ice made from water, dry ice doesn't melt into a liquid when it warms up. Instead, it undergoes a process called sublimation, transitioning directly from a solid to a gas without ever becoming a liquid. This distinctive characteristic creates that signature fog effect when dry ice is exposed to air. At a temperature of minus 78.5 degrees Celsius, minus 109.3 degrees Fahrenheit, dry ice is significantly colder than regular ice, which freezes at 0 degrees Celsius, 32 degrees Fahrenheit. This extreme cold makes it incredibly effective for freezing and preserving materials, but also requires special handling precautions. The name dry ice actually comes from its unique property of not leaving any wet residue behind as it sublimates. It simply vanishes into the air as carbon dioxide gas. This makes it particularly useful in situations where moisture is a problem. Before we can understand how dry ice is made, we need to know where the carbon dioxide comes from. The CO2 used to produce dry ice comes from various industrial sources. Industrial processes, such as ammonia and hydrogen production, naturally generate CO2 as a byproduct. Large-scale fermentation operations, such as those in breweries and ethanol plants, also produce significant amounts of carbon dioxide. Some facilities even capture CO2 directly from natural gas wells or power plant emissions. This captured carbon dioxide undergoes purification processes to remove impurities, such as water vapor, sulfur compounds, and other contaminants. The purification process ensures that the resulting dry ice is clean and suitable for various applications, particularly those involving food or medical use. Now, let's explore how this purified carbon dioxide transforms into solid dry ice through a fascinating multi-step process. Step 1. Compression. The journey begins with gaseous carbon dioxide being compressed under high pressure, typically between 20 and 25 atmospheres of pressure. Powerful compressors squeeze the gas molecules closer together, which causes the temperature to rise as a result of the increased pressure. Step 2. Cooling. The compressed hot carbon dioxide gas then passes through cooling systems that lower its temperature. Water-cooled heat exchangers, or mechanical refrigeration systems, efficiently remove heat from the gas while maintaining the high pressure. Step 3. Expansion and solidification. Here's where the magic happens. The cooled, pressurized carbon dioxide liquid is then allowed to expand rapidly through an expansion valve into a large chamber at atmospheric pressure. This sudden pressure drop causes a portion of the liquid, CO2, to flash freeze instantly into solid particles, essentially snow made of carbon dioxide. This process follows a principle known as the Joule-Thomson effect, where a gas cools when it is allowed to expand rapidly. When using a liquid CO2 feed source, approximately 40 to 50% solidifies, while the remaining gas is typically recycled back into the compression stage. Step 4. Compression into blocks or pellets. The carbon dioxide snow that forms is then collected and compressed into the various forms of dry ice that we use. For block dry ice, hydraulic presses compress the snow into dense rectangular blocks, weighing approximately 50 to 60 pounds, which are typically used for large-scale shipping and industrial cooling purposes. For dry ice pellets, also known as rice, The snow is forced through special dies or presses to create small, cylindrical or rice-shaped pellets. These smaller formats are preferred for applications like blast cleaning, food processing, or theatrical fog effects. While the basic principles of dry ice production have remained consistent, modern manufacturing has introduced several innovative approaches to improve efficiency and quality. The most efficient modern method utilizes specialized equipment that converts liquid CO2 directly into dry ice snow in a single step. These machines are often compact enough to be installed on-site at facilities that require regular dry ice supplies. Today's production facilities utilize advanced hydraulic block presses that can produce blocks with perfectly shaped edges and consistent density. These automated systems can manufacture hundreds or even thousands of pounds of dry ice per hour with minimal human intervention. For specialized applications requiring pellets or specific shapes, modern dry ice pelletizers can produce uniform pellets in various sizes. Some systems can even create custom-shaped dry ice products for specific industrial applications. Due to constant sublimation, dry ice requires special handling and storage considerations. Dry ice is typically stored in specially designed insulated containers that slow the sublimation process. Even in these containers, dry ice will gradually disappear at a rate of approximately 5 to 10% per day. Production facilities often manufacture dry ice continuously or shortly before shipment to ensure customers receive fresh product with minimal loss. For this reason, many large-scale users have on-site production capability rather than relying on deliveries. The remarkable properties of dry ice have made it valuable across numerous industries. In food preservation, dry ice keeps products frozen without the mess of melting ice. The food transportation industry relies heavily on dry ice for shipping perishable goods, particularly when mechanical refrigeration isn't practical. Medical facilities utilize dry ice to preserve biological samples and vaccines, particularly in areas where reliable refrigeration is unavailable. The entertainment industry utilizes dry ice for special effects, creating a low-lying fog effect that's ideal for setting the atmosphere in theatrical productions. Industrial cleaning operations use dry ice blasting, a non-abrasive cleaning method where dry ice pellets are accelerated toward a surface to remove contaminants without damaging the underlying material. It's worth noting some important safety and environmental aspects of dry ice production. While dry ice itself doesn't directly harm the environment, the energy required for production and the source of the carbon dioxide can have varying environmental impacts. When possible, using captured CO2 from industrial processes helps reduce the overall carbon footprint. Additionally, when dry ice releases CO2 gas, it can displace oxygen in poorly ventilated areas, creating potential suffocation hazards. For these reasons, proper handling protocols and ventilation are essential when working with dry ice. The production of dry ice represents an elegant industrial process that transforms gaseous carbon dioxide into a versatile solid with unique properties. From the compression of CO2 gas to the final formation of blocks or pellets, each step in the manufacturing process is carefully controlled to ensure a consistent, high-quality product. As technology advances, dry ice production continues to become more efficient, making this valuable material increasingly accessible for applications ranging from the practical to the theatrical. So the next time you encounter that fog effect or receive a package kept perfectly frozen with dry ice, you'll know precisely how that remarkable substance came to be. Thank you for watching another episode of Everyday Nuggets. If you enjoyed this episode, please like and subscribe for more videos. If you have suggestions for other everyday things you'd like to know about, please leave them in the comments below. Stay curious.